Hi, this is Kenny Lee. Let's talk about free fall problems where we get to do some of the math involved with this. First of all, when an object's in free fall, that means the only force acting on it is that of gravity. And so we're neglecting air resistance. Or we say air resistance is negligible. Or some phrasing like that to let us know that air is not going to be a problem. Now on Earth, the acceleration due to gravity is 9.8 meters per second squared. And we use it so much we actually give it a special letter. We call it a lowercase g. So lowercase g is always 9.8 meters per second squared. And we can still use our old kinematic equations, except the acceleration for each one would be 9.8. So on a lot of these problems, if something is dropped or thrown in the air or flung down or something like that, they usually don't give you the acceleration because they expect you to know the acceleration due to gravity on the Earth is 9.8 meters per second squared. Now, if you're on a different planet, then you have to either calculate the acceleration due to gravity or they'll have to tell you what it is. Let's look at this first problem. We've just got a ball that we're going to drop from a great height. They usually say that to make sure they have enough room. How far will it fall in 5 seconds? And what is its speed after 5 seconds? Well, here's the thing. They don't give you a lot of information here. We just know that time is 5 seconds. But we know a couple of things. We know that it's dropped. Anytime you see that it's dropped, we know the original velocity is 0. And since it's falling, we automatically know that the acceleration is the acceleration due to gravity, and that's 9.8 meters per second squared. And I've also seen this written as like a with a little g for acceleration due to gravity. But no matter how you write it, it's still 9.8 meters per second squared. Although sometimes we round it off to 10 meters per second squared to make the math a little bit easier, but I like to keep it at 9.8. So let's see what we're going to do with this. We want to figure out how far will it fall in its speed after that time. Well, let's figure out how far it falls first. So since it's accelerating, I have to use this equation. I can't use v equals d over t because it is accelerating. And since the original velocity is 0, that term goes away. We're just left with d equals 1/2 of 9.8 times 5 squared. And so if we start doing our calculations, we get 4.9 times 25, that it would have fallen a distance of 122.5 meters. Well, it also asks us to figure out its speed after that time. So that means I'm looking for the final velocity in that case. So I can do A equals VF minus VO over T. Acceleration we know is 9.8 meters per second squared. Final velocity is what we're looking for. Original velocity is 0, and our time is 5 seconds. So we just multiply across. 9.8 times 5 gives us 49 meters per second is the final velocity. Now there's one thing I need to say about this. Traditionally, we like to say up is positive, down is negative, right is positive, and left is negative. But we're not restricted by that. In this problem, everything was acting down. Acceleration was down. My velocities were all going to be down. In that case, I actually redefined this and said down was the positive direction. That's perfectly legitimate. You can say that down's negative and just use that as your reference frame. But I like to try to keep things as simple as possible. And as long as everything's going in the same direction, we'll just say that direction is the positive direction. Let's take a look at this one. We've got a feather is dropped from a height of 25 meters in a vacuum. Now, when it says it's in a vacuum, we don't mean a vacuum cleaner. We actually mean that there's simply no air resistance. We want to know how long does it take for it to hit the ground. Well, again, it's dropped, so the original velocity is 0, but it's also falling, so gravity is 9.8 meters per second squared, and that's the acceleration. And then we also want to find the final velocity the instant before it hits the ground. So we're going to go through a very similar process. I need to find a time and a final velocity. Well, I think I'm going to start off with this. I'm going to start off with A equals VF minus VO over T, where A is my acceleration due to gravity, 9.8. Again, since everything's going the same direction, I want to leave it positive. Final velocity, we don't know. Original velocity was 0, but we don't know the time either. Okay, we're kind of stuck on that one. Well, let's try the other one then. Let's look at the distance while accelerating. D equals V0t plus 1/2 AT squared. Well, our distance is 25 meters. It's being dropped, so the original velocity is 0, so that term goes away again. That's really handy. We got 1/2 of 9.8 times t squared, and we can solve for t, and then we can use it over here to find that. So we get 25 equals 4.9 t squared. Go ahead and let's just do the math. 25 divided by 4.9 gives me 5.1 for t squared, but we don't want t squared, we want t, so we're going to take the square root. And so our time is 2.5 or 2.26 seconds if I round off. Now that we know that, we can go back to that acceleration equation and plug that in to see what we get. So we get 9.8 equals VF, the 0 is not going to matter, 2.26. So 2.26 times 9.8 gives me a final velocity of 22.15 meters per second for that one. So we got stuck there, but we could figure out over here. Let's try one that's a little bit more elaborate. We got a ball thrown upward. Okay, now things are going to go in different directions because we're going to have the ball thrown upward, but gravity is acting downward. So we got two things working in opposite directions. So we're going to have to define one way as positive and one way as negative. I'm going to define up as positive, so that makes gravity or anything else downward negative. So a ball's thrown upward with a speed of 34.3 meters per second. We know gravity is acting downward, so that's going to be a negative 9.8 meters per second squared. How long will it take to come to a stop? So we're looking for a time for it to come to a stop. Well, it's coming to a stop. Well, that means the final velocity has got to be 0. And we want to know how far above that person's hand the ball is. So we're also looking for distance. Okay. Well, with this right here, I think I'm going to start off with the acceleration equation. A equals VF minus VO over T. So negative 9.8 equals VF, which was 0, V0, which is 34.3, and time, which we don't know. But we're going to do the super secret metric and swap those two out. So time comes out negative 34.3 over negative 9.8. So we get a time of 34.3 divided by 9.8. We get 3.5 seconds. So that ball is in the air 3.5 seconds to come to the very top of its arc up here. Took 3.5 seconds. Now we want to know how far up in the air that ball is. So for that we can use our distance equation. V0t plus 1/2 at squared. Plug in our numbers. We know original velocity is 34.3. Our time is 3.5 seconds. Plus 1/2, a negative 9.8. Don't forget that because we're throwing this up and gravity's acting down. In a time of 3.5 seconds, and that's got to be squared. Okay, so now we just use our handy dandy calculator. 3.5 times 34.3 gives us 120.05 minus, that minus sign is going to come out, 3.5 squared times, and that will be 4.9, 60.025. Then we just put those together, and I get a distance of 60.0, let's call it 3 meters above its launch position. Well, we got a secondary question over here. What will be the ball's height and velocity after 5 seconds? Well, it took 3.5 to get up here, so at 5 seconds it should be on its way down. But we're going to see what the math turns out to see if the math gives us any clues about that. Height and velocity. So I want to figure out velocity first. So A equals VF minus VO over T. Acceleration is negative 9.8. We still got to keep that convention. Final velocity is what we're looking for. Original velocity was 34.3. And we're looking at 5 seconds. So 9.8 times 5 gives us, that'll be a negative 49 equals VF minus 34.3. Well, we're going to add 34.3 to both sides. And so we get a final velocity of negative 14.7 meters per second. And that's okay because that means we were coming back down, so the velocity should be negative. So far, so good. Now let's figure out the height of the object at that time. We're going to use our distance equation. So our original velocity was 34.3. Time in this case is 5 plus 1/2 negative 9.8 times 5 squared. Okay, 34.3 times 5, 171.5 minus, because again that's going to make it negative, 25 times 4.9, 122.5. Well, we don't need a unit just yet. Distance of 49 meters. All right, so let's check one more problem. I've already got this one started. A rock is thrown downward, so it's thrown down. So everything's going the same direction. Velocity is down, acceleration is down. At 15 meters per second, we've got acceleration due to gravity and a time of 4 seconds. So I want to first figure out, well, what it asks first is, what's this acceleration right after it leaves a person's hand? Well, it's 9.8 meters per second squared. Anything falling, no matter how it got going, is going to accelerate down towards the center of the Earth at 9.8 meters per second squared. So, to figure out the distance that travels during that time, I've already got things set up. So all we have to do now is actually calculate that. So, we have got this will be 60 plus, well, 4 squared, 16. Take half of that, then multiply by 9.8. We get 78.4, and just add the 60 to it, we get a distance of 138.4 meters. It would have, if you just dropped it, only fell 78.4 meters, but because we threw it down and it had that initial velocity, it fell an extra 60. Now to find its velocity after that time, we just use acceleration. A equals VF minus VO over T. Acceleration is 9.8. Final velocity is what we're looking for. Original is 15. And we have a time of 4 seconds. So 9.8 times 4 gives us 39.2. F minus 15. Add 15 to both sides, and we get a final velocity of 54.2 meters per second. All right, those are some problems having to do with acceleration due to gravity near the Earth. Hope you enjoyed the video. Tune in for some more.